Good afternoon, ladies and gentlemen. Welcome to today's Taiwan Bridges keynote speech in Academia Sinica. We are honored to host today's session, which features insights from Dr. Michel Mayor, the 2019 Nobel Laureate in Physics. Before we proceed, the Vice President of Academia Sinica, Dr. Mei-Ying Zhou, will deliver the opening remarks and formally welcome the speaker. Please join me in welcoming Vice President Zhou.
Okay, our distinguished guests, colleagues, ladies and gentlemen, good afternoon, and welcome to Academia Sinica. It is a great pleasure to have you join us at this fourth lecture under the Taiwan Bridges program here at Academia Sinica. Taiwan Bridges is an international initiative facilitated by the International Peace Foundation and designed to connect Taiwan with the world by bringing leading thinkers, Nobel laureates, to visit Taiwan. Through these lectures, we hope to foster dialogue on fundamental questions that shape science, humanity, and our shared future. We're deeply honored to welcome Professor Michel Mayor, Emeritus Professor at the University of Geneva and recipient of the 2019 Nobel Prize in Physics. In 1995, Professor Mayor made a historic breakthrough with the first discovery of a planet outside our solar system. This discovery demonstrated that our solar system is not unique in the universe and opens the possibility that life may exist elsewhere in the cosmos. So on behalf of Academia Sinica, I would like to express our sincere gratitude to Professor Mayor for joining us today and for sharing his insights and with our academic community and the general public. Next, the moderator of today's session, Director Wei-Li Peng, from the Institute of Astronomy and Astrophysics here at Academia Sinica, will introduce Dr. Mayor and his scientific achievements. Thank you very much.
Thank you, Dr. Zhou. And Dr. Mayor, fellow guests, it's my honor and pleasure to be able to introduce our outstanding lecturer today to learn about the recent developments in our universe. I remember when I was a student, there were 9 planets in the universe. Meanwhile, one of these planets, Pluto, is no longer a planet, so we're having fewer and fewer planets in our universe, you might think. But it was completely clear in 1995 when we read about the discovery, and I must say, to me, it was very unexpected, even though I was a PhD in astronomy myself, that there were planets around other sun-like stars. And it was immediately clear that this changes it wasn't known, right? We had the sun with the Earth, yeah, sure, there and 8 others, but nobody really knows if this is typical or strange, and suddenly we know that we are not alone, certainly not in the sense that there are planets in the universe, and this is a huge change. It's like Galileo and Copernicus understanding that we're not the center of the universe, and now we're even less the center, so this has been a huge conceptual change, certainly to us astronomers, and I hope for everyone to see how we went from 9 planets to 6,000 and more and growing today. And I think I'm very much excited to hear from the discoverer the co-discoverer, Dr. Mayor, and we already heard a lecture 2 months ago from his former PhD student, Dr. Kelos, about the story of the discovery and where this might take us. And this is a very profound question I'm sure all of us have at least dreamt about or thought about, and to actually hear about what may happen someday seems like, what more can you ask for? Thank you. Let's welcome Dr. Mayor.
Ladies and gentlemen, thank you very much to have the possibility to discuss with you one of my hobbies. It's a very new domain of astrophysics and plenty of dreams. And I will try to answer this question here. What is reasonable in this domain? We are not the first to think about these questions. It's very impressive to me that already more than 2,500 years ago, Greek philosopher was already discussing the possibility of what is called the plurality of worlds in the universe. And in a very famous letter of Epicurus 3 centuries before Christ, in the same letter, he expressed his vision that we have an infinite number of worlds in the universe. It was a philosophical question, the worlds, it's not exoplanet. But in the second part of this letter, he expressed his dream that living species could exist on some of these worlds, but not on others. So 30 years ago, we have proven the first part of these two sentences, and in front of us, we still have the second part of this question. But it's really impressive. And it was not only a philosophical dream. In fact, all these stories start from the work of Democritus. Then the matter is formed by atoms. So if you have a piece of iron, you cut, it's 2 pieces of iron, you cut, and so on. And at some moment, you are left with a small piece with all the characteristics of iron, but we cannot cut it. It's atom. And these philosophers say, if the nature is built from atom, why it will only form only one world? We can form many others. So this was the root of this philosophical vision. And in fact, this was not limited only to the world of the Greek philosopher. In fact, during all the 2,000 years later, you have a lot of theologians, philosophers, and then scientists having expressed opinion on this domain. And I will only mention 2 of them. One is the philosopher, the German philosopher Albertus Magnus, and he said, what is most important to discuss this question? This is one of the most exalted questions in the study of nature. And I will finish with this historical introduction with the mention of Giordano Bruno. Giordano Bruno was not a scientist, he was a monk. And he wrote a book on this question. And he said something very, very simple. He said, the sun is a star. For us, okay, it's something very, but at the time it was not so evident. And the sun is brighter only because it's closer to us. And if we have planet orbiting the sun, we should have planet orbiting other stars. And at this time, is no more worlds, it's exoplanet, it's planets. This was in the 16th, okay, it was killed, it was burned in Roma in February 600, but not for other reason, for theological reason. And not for, but this is absolutely, it was absolutely clear, it was absolutely modern view of what it is. Okay, modern. view. This is a real picture of a very teeny part of the Milky Way. And you see that it's not the problem to find new stars. We have plenty of stars, it's not the problem. The problem is to say, do we have planet orbiting this star here, or this one, and so on? Is it possible to do it? Is it a completely crazy dream or not? How many planetary systems do we have? And this is incredible to see the change of paradigm existing last century. But before to discuss this change of paradigm, I will just, after the vision of Giordano Bruno, it was, this idea was extremely popular in the public. And here you have a picture of the atlas of the 17th century, 18th century, and you can look on the upper right corner, and you see that the distant stars are already surrounded by planetary system. So it was very public, this idea. And you have other illustration possible. And in the beginning of the 20th century, this was August 1940, and you see that you have plenty of fictions with exobiology people of some kind, in a very bad place. Callisto is a satellite of Jupiter. Is certainly not the best place to have. But okay, no, you see, this for the general public, people was very used to dream about exoplanet and exolife. But if you are looking at the literature of astrophysics, this is only the first part of the 20th century. The difficulty was the fact, for the astrophysicists, was the fact that you need the formation of an accretion disk, or disk, a nebula of dust and gas. And what is the mechanism to form such a disk? And during the first part of the century, it was only if you have two stars crossing each other at very close, small impact parameter, you can, by tidal interaction, form a disk orbiting around the star. But the probability to have such an event is extremely low, is very close to zero. Let's imagine, it's a typical exercise for students in astrophysics. If you have 200 billion of stars in the galaxy, moving during 10 billion years, how many close impacts do you have? You can do the statistics, it's nothing. It's close to zero. So no way to do it. And the net result of this estimation, that's a very important astronomer. You have Sir James in Cambridge, Shapley in Harvard, and so on, estimate the number of other exoplanetary systems in the Milky Way was zero. We are alone. And this was completely opposite to the fictions we can dream and so on. The astrophysics do not believe that we have other planetary systems in the Milky Way. And then, after you have a small letter, I like to repeat this citation by Otto Struve in 1952. He was working in a completely different domain. He was simply measuring the rotational velocity of stars like the sun. And he was expecting always to have very fast rotators. Because when you form a star by collapse of gas, in fact, you have always a large excess of angular momentum. And so he was expecting fast rotators. And as you maybe know, that in fact, all the stars like the sun are extremely small rotators. The velocity, the rotational velocity is very small. And he concludes correctly in the abstract. Therefore, because it says the angular will move to form the disk, and this, therefore, they can many planet-like objects in the galaxy. So this is a small letter. It's not a long paper, no calculation, no physics, and so on. It just do this remark, and this was really the start of the completely change of paradigm. And this is completely motivated by all the studies made during the last century on the formation of stars. In fact, this is a real picture. It's not a nice painting, modern painting. It's a real picture of astrophysics. And in fact, you see this is really a very complex, difficult domain, because you have a huge contrast of density between different places. You have a lot of motion, you have magnetic field, you have young stars, and so it's very difficult. But when you have the collapse of this matter, of turbulent gas, you always have a huge excess of angular momentum. It's not a detail, it's a really huge. The contraction is something 10 to 20. It's a huge increase. So this, it was not so long that we realized that we have new stars form in the galaxy. So this is almost at the same moment I mentioned before for the change of paradigm. So, and here this is a full diagram after the 20th century, that the first part was 0, something like this, and suddenly you have a jump of something like 10, 100 billion of the probability to have planetary system in the Milky Way. This was really the start of this possibility to dream to detect other exoplanets. And you see, and the present situation, the statistics of the discovered planet is really at the level of 100 billion planetary system in the Milky Way. And this was first, this disk was first discovered as an excess of infrared luminosity on young stars, but the most evident demonstration of this planetary disk was provided by the Hubble Space Telescope in the 31 years ago. Here is Orion Nebula, and you can see that you have quite a lot of young stars going out of the nebula, and the Hubble Space Telescope with its extreme high resolution was able to look the possibility, the fact that we have this dark disk of matter orbiting stars. Because why? Because the disk of dust blocks the luminosity coming from the nebula. So this was absolutely evident, and most of stars, if not all, have this kind of thing. This is really the nursery for the formation of planets. And also, evidently, we are a byproduct of the formation of stars themselves. So here you can see the north of Chile, 5,000 meters of altitude. You have this huge altiplano, and I heard recently some of them are working yourself here in this place. You have all these dishes of 12 meters of diameter, 60 dishes, looking in the same place of the, all together, looking in the same place of the sky. And then after you can combine the luminosity received of this interferometer in the special computer in the middle of the net. You can expand this network up to 14 kilometers to have the highest resolution. And evidently this is a good way to study cold matter in the universe. It could be formation of galaxies, stars, planets, and so on. It was something like 20 years ago. And it's the most evident question we can ask. Here you have a small cloud, much smaller than the Orion Nebula. And we knew that we have two stars, young stars formed in this nebula, and we can ask to look with the interferometer, and what we see is the formation of a full planetary system, because you have the disk of dust, and when the young planet is formed, the planet will accrete the matter in a ring, and you see all this ring may be formation, they're related to the formation of the planetary system. You have a second one here. It's interesting, but it's seen on the perpendicular, so you cannot see the disk, but you have a jet, and so on. This is a story of the formation, the complex story of formation of planets, planetary system. And evidently, this colleague, having made this kind of research, have continued to study young objects, and this is extremely common. In fact, we planetary system, we are a byproduct of the formation of stars themselves. So the net result that we can expect a huge, huge amount of planetary system in the Milky Way. Oh, we can look again the same picture, but the question how we can detect planet orbiting. Despite the fact that the probability is very, very high, it's almost impossible to see a planet close to a closest star, because the ratio between the luminosity of the star and the planet is so huge that you are completely dominated by the luminosity of the star. So no way to directly see the small planet close to one of the stars. So you have to develop indirect technique, and the most evident one is to measure the velocity of stars, the star. When you have the system with the star and the planet, you cannot see the star, but you can notice that you cannot see the planet, but you can detect maybe the motion of the star orbiting around the gravity center. And you see we are lucky enough that the spectrum of a star is a huge forest of atomic transition. It's maybe, I don't know, 600,000 is visible or something like this. So the Doppler effect will create an oscillation of this forest due to the Doppler effect, and you can see the change of the velocity induced by the gravitational influence of the planet. And it is what we have used 30 years ago, first by developing a new spectrograph with colleagues of France and with a relatively modest telescope, 2-meter telescope, and we have detected this. It was completely unexpected after only a few months of measurement. You have the velocity versus the time, and you see that sometimes the star is moving in your direction, sometimes receding, and so on. And okay, the precision at the time was not exceptional. No, we are much, much better than this. But what was the surprise of this area? First, do we have a planet or not? It was not sure, because this object was orbiting, the estimated mass was only half the mass of Jupiter, so a giant planet. But with a period so short, it's 4.2 days. So let's imagine Jupiter orbiting the Sun in 4 days. And this was in disagreement with the theory by a factor 1,000. So 4 days versus 10 years or something like that. So because the theory predicts that to form a giant planet like Jupiter, you need to accrete ice particles. The ice particles do not exist close to the star. So this was, but today, with this technique, all the people having, it's not only one place, something like 6,000 planetary systems have already been detected during the last 30 years. So evidently, having started with a small telescope in the northern sky, we say maybe we can move in the southern sky with a better climate, and we have developed a new instrument, maybe, no, not maybe, much better, much more precise, and so, and working on a 3.6 meter telescope in Chile, in La Serena Observatory. So we got a huge amount, having developed this instrument, we got as a reward a huge amount of observing nights, 500 nights during 5 years. So it's absolutely incredible. And we start the survey. Here you have a plot where the mass versus the semi-major axis. So here you have the distance between the sun and the Earth, 1/10, and so on, 10 times more. And you have the different planets of the solar system. And now you can notice the different discoveries we made. So 51 peg, very close orbit. And then after, you see in red all the discoveries made by radial velocity technique, the Doppler spectroscopy. And you can see new objects with different colors. And this is related with the development of new techniques. For example, the transit photometry, we will discuss again. This is important for the future. It's probably most important. The probability favorize the discovery of short period. And this lack of object here is not real, is only a bias due to the techniques we are using. And you can notice, for example, the present techniques are not really sensitive to the detection of Earth or Venus-type planet. And also you can see microlensing, this is gravitational effect, and direct imaging for the very massive distant object. This is maybe not object suitable for the formation of life. So you see, it's impressive, the number in few years, how many planets. And evidently, this was the observational aspect, but the theoretical people work as though to try to explain. And why we have this discrepancy of 1,000? When you have the formation of young planet in a disk, you have a gravitational interaction between the planet and the mass of the disk, and you have a shrinking of the orbit. And this will be explained by the simulation made by some colleagues from Bern, but also from Japan and US. You see, you have two competing effects. The accretion increases the mass of the star, but also this moving, the shrinking of the orbit. So this explains why we do not have all systems like the solar system. In fact, we have these two very important phenomena to explain the diversity of planetary systems. And just to have an idea of the present, I will not discuss all the 6,000, but only a system very close to us. Proxima Centaurus is the closest star to the sun. The distance is only 4 light years, only. And you see already two planets have been discovered, but very, very close to the stars themselves. One with 5 days and one 10 days or something like this. But what you can notice already is that the Doppler spectroscopy is already able to discuss and to detect objects much smaller than the Earth. Okay, but very close to the star. So next, the second technique. In what it is, 27 years ago, we have discovered a planet with an orbit a little bit closer to the star, where the period is only 3.5 days. So if you have the star, you have the planet orbiting like this. But if the plane of the orbit is exactly in the direction of your eyes, you have the possibility to have a small eclipse. We are using the terminology of transit. So when the planet crosses the disk of the star, you are expecting to have a small dip, a small drop of the luminosity of the star. It's very simple. It's absolutely simple. After it's a very simple geometry. The size of the star versus the size of the size of the planet versus the size of the star. So the contrast is a direct measurement of the size of the planet. And so when you see, we have predicted from the velocity at what moment we can expect to have this transit. We ignore the inclination of the disk. So we are not sure that if the disk is correct, and exactly at the time predicted, we were collaborating with colleagues in Boulder with a small telescope. It's only 10 centimeter telescope as a hobby in a garage. It's not a professional one. Exactly, we have the drop of luminosity. And when you do the calculation, we have the mass of the star, we have the size of you have the mass of the planet, you have the size of the planet, and you derive immediately that the mean density is only 0.3 grams per cubic centimeter. It's half the density of Saturn. So this was a direct proof that it is a gaseous giant planet. And this is the same measurement repeated 1 year later from the Hubble Space Telescope. And what you can notice when you are above the Earth's atmosphere, the huge precision you have, and immediately you see what I can do, what we can do better. And here you have the harvest of the Kepler space mission. The Kepler mission is a telescope of about 1 meter. The idea is very simple. You have the Earth here, you have Kepler. You look as part of the sky where you have something like 100,000 stars. You take a picture with a CCD, and you continue every half an hour. You take a picture. And then after 3 years, or something like this, you have 100,000 light curve. And you analyze this light curve, and you can notice that sometimes you have here, let's say here, you have an object with a very small contrast, small mass, small size, and a certain period. It's a 1 day. Okay, very close. 10 days, 100 days, and so on. So all the black dots correspond to one planetary system. But what you can notice, some of them have different catalog. For example, you have few objects with 6 planets orbiting the same star. So you see this, all the colors are coding different kind of multiplicity. So this is a direct proof that multi-planetary systems absolutely the rule. Because you are missing all the objects with the bed of inclination of the disk. So this is only the top of the iceberg. It's just the top. And you see, it's absolutely fantastic measurement. And once again, the missing part here is only due to bias. And here, evidently, the Hubble Space Mission gives access to the size of the planet, but not the mass. But if you want to do physics, you need at least to have these 2 parameters. And so it's the reason why we have a huge collaboration made with another telescope in La Palma in Canary Island, where we focus the time we have to measure the low mass object here. And you see the different curve correspond to different composition of the planets. And you see all the symbols correspond to measurement, Earth, Venus. You have all these objects, and you see that we have discovered quite a lot of rocky planets already here. And I remember when I was student, the classical view that it was already difficult to explain the formation of a rocky planet like the Earth. And here you can much more massive object than the Earth. So this is really the way to detect rocky planet and maybe later in the habitable zone. But what is the most exciting thing for the future? Okay, here it's a growing design. You have the star here, you have the orbit of the planet. When the planet is in front of the star, you will have a small dip of the luminosity, so you have the possibility to determine the size of the planet. When you have the planet behind the star, you have a small drop of the infrared luminosity, and this gives access to the temperature of the atmosphere of the planet. But what is the most exciting is this small blue ring. And this is a filter of the atmosphere made by the atmosphere of the planet. So if you compare the spectrum, when the planet is in front or behind, you have a small difference, but it's very tiny difference due to the filter of the atmosphere. And when you do this, you have a spectrograph. It's a free spectrograph for free given by the nature. And the question we have behind, is life a cosmic imperative? Do we have life everywhere in the universe when you have the good condition? Evidently, when sometimes you don't have the good condition. But if you have the good condition, is life an emerging process, normal in the development of the universe? But just to keep in mind the difficulty, this is a real picture of the sun. Remember, the sun is affected by a lot of magnetic activity, spots, eruption, convective zone, and so on. So you have always a small amount of noise due to this fact. And at the same scale, in the rectangle here, in the middle you have a small blue dot, is the size of the Earth at the same scale. So let's imagine we have the transit of the Earth in front of the star. It's a very small effect, completely affected by the convective things and so on. But also you have what is the impact of the Earth on the motion of the sun is only 8 centimeters per second. So you need to develop spectrograph able to detect small wobble of the forest of atomic line at the level of 8 centimeters per second. So, okay, it's possible. Our last spectrograph at the top of Paranal Mountain achieved something similar to this precision. But the real problem is the noise due to the magnetic activity. Well, this is just to give the difficulties of this kind of things. So, no, evidently, as you know, the Hubble Space Telescope was replaced by the James Webb Telescope. It's a larger telescope, 6.5 meter telescope, but coated by gold to measure in the infrared with some shoulder to screen to prevent the luminosity of the sun and Earth. So this is a beautiful experiment. And evidently, exoplanet is part of the different goal of this instrument. When I say it's a part of the program of the James Webb, I discussed with some people involved in this event a third of the telescope time is only devoted to this new chapter of astrophysics. It's incredible that this chapter, not existing 30 years ago, today is need a third of this beautiful experiment. So cold Jupiter, like us, hot Jupiters, like 51 Pegasus, the first one, mini Neptune. It's strange. Neptune is something like 10, 14 times the mass of the Earth, is very far. It's here. But you see the huge population of Neptune-type planets we have in the universe. We do not have this in the solar system. And evidently, for the question of life, we are very interested in rocky planet and planet with the mass of the Earth, so something similar, and with expectation of planets with a reasonable temperature. We do not have at the present time real solar type analog with a good temperature, but we can start to measure first the temperate rocky planets. And I repeat the same graphic we have before, and this is the effect, the detection of the atmosphere when you have a transit, and when you compare the star with the planet in front or behind, and you see the size is not the same in different colors. Why? Because the opacity of the atmosphere is not the same in different wavelengths. So if, let's imagine you are measuring a wavelength where the medium of the atmosphere is very opaque, the planet looks like this, and you have a very contrasted deep. But if the atmosphere is not opaque, the planet will look much smaller. So you have difference depending on the wavelengths where you are measuring the contrast of the transit. And this was first made from the ground, but eventually in the space you have the capability to do measurements in the infrared. And this was made already a few 3-4 years ago with a star called VASP-39. It's nothing, but you see these are the same stars, the same transit, but with different colors, different wavelengths. And you have teeny small changes depending on the colors. And you can see, if you analyze, this is the full spectrum you have. So it's so simple. You see that the ordinate here is simply the contrast of the deep. For this star is 2%, 2.1, and so on, 2.2, and so on. So the changes are at the level of the thousands. It's very small changes, but you can see all this information you achieve. And for example, here you have the carbon dioxide signature, huge quantity of carbon dioxide in this atmosphere and so on. So the dream of this kind of experiment is to have enough photons to detect biomarkers. So molecules, signature of molecules involved in the life chemistry. At the present time, this is not made, it's not possible, but evidently we are in construction different big telescopes with a size up to 39 meters of diameter. So telescope much larger than this room here. So you need a lot of photons, so you need big telescopes. Here I will discuss a dream. Is it possible to see an Earth-type planet in the habitable zone of a solar-type star? At the present time, it's not possible. How is it possible? The contrast of the luminosity is 10 to the 10. So it's really, really, really difficult. So for the future, The idea is maybe to implement a star shade at here, 99 meters of diameter, with a special form to try to take into account the diffraction of the star. And then after to put the satellite at some distance, 170 kilometers, and then after you can block the light coming from the star to see the planet close to it. And it's possible. The ratio of the luminosity achievable by this technique is 10 to the 10 or better, depending on the wavelengths. So I don't know how many years we need to do it. Certainly I will never see the results of this experiment, but it's possible. It's one possible for the future. You have other possibilities, but this is one possibility, and you have a paper in press describing and giving all the possibility. And this is combined with the big telescope and the ground. You have 3 big projects at the present place. So once it is detected by this space experiment, you can do it completely from the ground with big telescope to do the spectroscopy. So it's possible, not tomorrow, it's possible. So it's time to start and discuss the question of the title of this evening. So before going to exoplanet, just, okay, you have a lot of things discussing. For Elon Musk suggests that he dreams that in the next century we will have 1 million people emigrating from the Earth to Mars. Okay, just remember, the atmosphere of Mars is only 2% of the Earth's atmosphere pressure. It's no oxygen at all. It's carbon dioxide, argon, and so on. The ground of the soil of Mars is toxic. It's perchlorate. So it's not possible. Okay, it's absolutely possible to send few people, and I believe it's a dream, to send, like we have Apollo 11, send, a few teams doing measurement, but they will not cultivated salad and things like this. No, they will not walk and 1 million people. And so obviously you have fictions that you can terraform the ground. Yeah, but the mass of the atmosphere is huge, huge. If you want to produce, by chemical process, produce an atmosphere with sufficiently quantity of oxygen, it's not possible. So it's nice in papers, but it's absolutely not. I do not believe one scientist believing in this possibility. Few people, okay, not easy, but it's possible, but not an immigration. Okay, so this is not an exoplanet. But no, because you have some statement like, this is the first step to go like further. Yes, so going. So remember, we are living in the Milky Way. The Milky Way, the light will need something 100,000 light years to go from one side to another. It's big. The light need only 1 second to go to the moon, 8 minutes to go to the sun. So it's not possible to put on the same picture because it's too small. So few million of rocky planets in the habitable zone. The rocky planets are the easiest one to be formed. So if you have, we have detected so many planetary systems, it's evident that you have a huge, huge amount of rocky planets. All the theory observation shows that we have plenty. Okay, we do not have rocky planets at long periods, but we have a huge amount at short periods. So it's evident we have a huge amount of rocky planets, and some of them will be habitable. Okay, this is in near future, a huge domain of development. But take one hypothetical detection. Let's imagine that in the few years it's going on. We will detect a perfect planet, habitable at 30 light years. So it's a neighbor. We can not put on the preceding picture because it will be too close. So it's a real. Let's imagine we have the luck to detect such an object. At the velocity of Apollo 11, we will need several million of years to go to, because 30 years is 1 billion seconds. So it's already, this neighbor is already 1 billion times further than the moon. So, okay, you are optimistic, you say, okay, Apollo 11 move at 11 kilometers per second. So it's only a matter to accelerate. But maybe if you are driving a car, you know that when you accelerate, you need energy. But here, it's not a matter of two. You need to increase the velocity to close to the velocity of light. If you don't dream to have a million of years of travel, where you take this energy? It's energy comparable to the total quantity of the energy used on life, on the Earth. So impossible. At the present time, I don't see any possibility to accelerate this rocket. So if Earth starts to be inhabitable, in fact, we are unlocked on this planet, and the only reasonable things we have to take care of for Earth, I believe we will never emigrate. So we are humans on the Earth. Okay, sorry if I cut the dream. No, but okay, you have absolutely nice fictions. You have Star Wars and so on. Okay, you have rockets from one galaxy to another one. It's nice, but it's not physics. Thank you.